Today is Cameron Freer from Gamalon Labs, from Borelium Corporation, who will tell us about 3 problems in computable probability theory.
Thanks very much. The things that I'm going to be talking about today are joint work and various combinations with Nate Ackerman, who's here, Jeremy Avigad, Dan Roy, who will be speaking on somewhat related things on Thursday, and Jason Root. Okay, so I'm going to talk about 3 problems. They're somewhat related. Each of them is either an object or a result in probability theory for which we're going to ask about the computable content. So you can view this as a collection of results in what some people call computable analysis. And it also, each of these problems has some direct relevance to probabilistic programming languages and their semantics and various questions related to those. So the first thing that we're going to look at is de Finetti's theorem, and specifically the mixing measure, sometimes called the de Finetti measure. Then we'll talk about a higher dimensional version of it, Aldous-Hoover-Kellenberg theorem, which is also related to graph limits if you're interested in that perspective. So this is dealing with exchangeable 2-dimensional arrays in the case that we'll look at. And then the third example of a problem that we're going to look at is related to conditional probability distributions, and specifically the disintegration map that can be used to form conditional distributions. Some of these are positive results, cases where we're able to get objects that are computable even in situations where it's not obvious at first. And then some of these are negative results where we'll show the non-computability and in some cases calibrate that. Okay, so first we're going to look at de Finetti's theorem. And so I'll start with an example of an exchangeable sequence, but described in code. So this example should be familiar to some people in the probabilistic programming community, or also maybe who have seen it in a statistical context. So this is a sort of invented Python probabilistic programming language here. So the idea is, here's one representation, which is inherently sequential and uses state. I'll walk through what this does, and then I'll show you another representation that gives essentially the same thing in distribution, but is a rather different way of computing it. Okay, so we're defining a function here called nextDraw. There's some global variables, sum and total, and then we flip a coin with the weight determined by the ratio of sum and total, and increment some counters and return a value. So what's going on here is the standard Poyet-Earn, where we start with, in this case, 1 red ball and 1 black ball. Let's say the sum is the number of red balls and the total is the number of red plus black balls. And the way this urn works is we choose a ball uniformly at random from the urn. We look at it, we write down either 1 or 0, depending on its color, as the next element of the sequence. Then we put it back, and we also add a new one of that same color. So over time, this is going to drift towards what the ratio has been so far, roughly. So here's one example of a sequence of calls to nextDraw. Okay, so we get some sequence of 0s and 1s. Here's a picture of this path. So we're just plotting total versus sum. So this is sort of showing over time the state of these 2 variables for the sequence of nextDraws that we saw above, which is incrementing these global variables. Here's a different run. I haven't shown the separate 0-1 sequence, but there's some other sequence of 0s and 1s that gives this blue sequence. And there's a key property here that we'll come back to, which is that both the value of sum and the value of total are the same at the end of each of these runs, even though they had different intermediate values. Yeah?
So I want to understand this example. So then as a next draw,
yeah,
we'll move it in the same direction. So are you favoring the 0 and 1 final outcomes?
The same direction?
The same direction as the previous sum?
Oh, well, so sum and total are, so sum is sometimes incremented, and total is always incremented. So they both increase as you call nextDraw. So when we get 0, then that means that total was increased, but not sum. Then on the next one, we got a 1, so now they're both incremented. So they both tend to increase over time.
So if sum happens to be more than half of the total,
yeah,
then do you get with a higher probability of 1?
Yeah, exactly. So the ratio with which we get 1s tends to drift to the current ratio, where at the beginning it doesn't matter as much, but eventually after we've seen quite a large number of 0s and 1s, then it's very difficult to have the long run frequency be other than what it's been so far. Right, so
with half probability you should actually converge to, I mean the ratio should converge to 0. the ratio between sum and total?
No, it's more complicated than that. So here's a picture of what happens with the longer run. So this box here is zooming out from this original here. So this is what happens when this red run is continued in one possible sequence of coin flips. And here's blue continued. So they both go through the same point there, as we observed. So they both have the property, as I said, that there's a long run limiting ratio. And in fact, with probability 1, that happens to an infinite sequence of draws. But the particular slope, it turns out you can show, as Poya analyzed, that that's uniformly distributed. So uniformly between 0 and 1 is the distribution of the limiting slope, which almost surely exists for this particular example. So it's a little bit surprising. Okay, so this is what's going on with that example. This is a sort of standard sequential representation of the Poya urn. Now I'll describe it in a rather different way, but if what I just said, what I just claimed is true, then this should give the same distribution. So here we first draw, outside of the procedure, a uniform random variable, theta, just once. And then next draw has access to theta, but it doesn't use any state, it doesn't change any state itself. It doesn't store anything at the end of its run. It just independently, each time, draws Bernoulli with weight theta. Okay. So it turns out you can show that these have the same distribution over a sequence of next draws. So you might think this is a one-off case, but in fact, de Finetti's theorem, which I'll describe in a moment, says that in fact, whenever you have some possibly sequential representation that has the property that the sequence of random values you get is invariant in distribution to rearranging the terms, as you can show for this, then in fact there has to be a representation essentially like this. So I'll make that more precise now. Okay, so a bit more formally, we'll talk about a sequence of real random variables, though you can do this in a Polish space without too many modifications. So we say it's exchangeable if for each n and every permutation of 1 to n, the joint distribution of the first n terms of the sequence is the same as the permuted distributions. The joint distribution of the permuted terms in the sequence. Okay. And you might wonder about whether this holds for infinite permutations. In fact, that's automatic by Kolmogorov consistency, but we don't need to worry about that in any particular finite run, but in fact that's true. And so de Finetti's theorem says the following are equivalent. So the sequence is exchangeable. It has this symmetry property. If and only if the sequence is conditionally IID given some random variable theta. So here, this was that uniform random variable. In general, this is going to be something like a random measure. You can think of, in that case, it's a random Bernoulli, where we just specified the random parameter explicitly. And a third representation, and we'll give yet another in a slide or two. So a third representation is that the entire sequence, the infinite sequence, is equal in distribution to the following sequence of function calls. So there's some function f, a deterministic function, such that when you give it uniform random variables as inputs, where the theta is shared across all of them, and the ui's are different, so these are each marginally uniform and they're all independent from one another, then this is equal in distribution. Okay? So that's essentially what was going on in the second representation. We had this theta that was being shared across all of them, and each of them used some, well, the uniform that they were each using was sort of implicit in the coin flip. It could have been something more complicated. But there's always a representation of that form abstractly. This doesn't mean that there's necessarily a computer program to do it, but this is what the theorem is saying. Okay, are there any questions about this so far? Yeah.
I'm not sure. So you're saying the previous example, the Polish urn, it's exchangeable?
Yes.
So that means that if I have one sequence that have zeros and then have ones, and the other sequence is 0, 1, 0, 1, 0, 1.
Yeah, so what you can show in the case of the Polya urn, a key property that implies exchangeability in this particular case is that the probability of any particular prefix is determined only by the number of zeros and the number of ones. So if I tell you what sum and total are, you can tell me the probability of that sequence. You don't need to know the particular order.
Just these two sequences. One is 0, 1, 0, 1, 0, 1, so that has probability like 1/2 to the n roughly, right? Because each time we'll have about...
Well, it's more complicated, right? Because the coin flip each time depends on this value that's drifting.
It's about 1/2 in each step.
Close, sure.
And the other one is all zeros and then all ones, which will be very different.
They're the same.
It turns out they're the same. So there's a calculation to be done that I'm not doing, but yeah, it turns out that they're the same. I mean, there's maybe other ways of describing this that make it more obvious. I'm not claiming it's clear in this case, but it happens to be the case. You can write down, for example, a closed form, and then it's clear. Okay, so we're asserting that this is exchangeable, and this is a sort of instance of Finetti's theorem, but I'm not claiming that you could have found this automatically. This is just happening to be the case. Okay, but then the question that we're going to look at is when you can actually derive something on the right from something on the left. Okay, so I'll just pause for a second to note an additional interesting property, maybe more from either the statistical or programming language point of view, which is if we consider these sequences as represented in the two different ways as a graphical model or BaseNet, what's going on here with the conditional independencies that are implied by these arrows is that the sequential representation, we generate y1 using some randomness, then y2 conditioned on y1 again uses some randomness, and then y3 depends on the value of y1 and y2 in principle, and again uses some randomness and so on. So it's a very complicated conditional independent structure in the sequential representation, whereas quite explicitly in this either this third point or just the conditional independence is stated explicitly in number 2, it's saying there's some random variable conditioned on which they're all independent. So this is some sort of shared object such that once you know that, it can be computed in parallel. All right, so these are rather different structures of the computation, even though it turns out they're the same in distribution. So informally, we might say that using the function f, we can sample the variables yi in parallel. Okay, yeah. Mm-hmm.
In the preceding slide, what happens if you start with a different proportion of red and blue?
Okay, yeah, so that's a good question. So it turns out that if you start with any value of sum and any value of total that are, I guess, positive, and with total at least the value of sum, what you're going to get over here is the beta distribution of appropriate parameters in terms of these. So if you start with R red balls and B black balls, then it's beta of RB. So I guess in this case it would be beta of sum comma total minus sum. It happens that beta of 1, distribution is uniform on the unit interval, which makes it sort of simpler to describe this. But not only is there a limiting long-run frequency with probability 1, but in fact the distribution of those limiting long-run frequencies itself has a nice closed form in terms of these two parameters, which don't even have to be integers.
Maybe one way to address the seeming paradox you were seeing is that if you condition on, so these two paths, the red and blue, end at the same point. They have the same probability. But there are many more paths that have kinks. And there's only one path that has only one kink. So I think you're kind of latching onto the fact that it's rare to have it end at that point and go flat and then come up.
What is a kink?
Like the zigzags. Yeah.
Zigzag.
Right.
The angle in that line.
Yeah, so some of these pictures are more common if you consider various simple rotations of them to be the same picture, but still in aggregate, yeah. But they're all equal in probability. Right.
So if I think about this as a Markov process, then essentially what you convinced us is that any distribution is a stable distribution. It's a Markov process between the 0 and 1 values of the variable y. So you have two states, y can be 0 or 1. Then any probability on these two states is a stable probability distribution of this Markov process. Because if you're with probability p and 0 and with a probability 1 minus p and 0, p and 1, then your Bernoulli there uses exactly the same probability distribution for the next round. So it's a stable distribution. Just an observation.
Only in the limit.
So this theta is the limiting value, but it doesn't literally appear at any point here. Like if you stop this at any given finite point, still the conditional distribution of the next term, like that predictive posterior, is determined by just that initial prefix. So
it's a Markov process. So it's time t plus 1 depends only on.
It's not Markov.
It's not Markovian because you have to look at all the things that happened before.
It's
right?
conditionally Markov.
Right.
yeah, conditioned on this variable, it's Markov, but that variable doesn't even exist over here. I mean, it's implicit, but yeah. Okay. So So then the question is whether we can move between the representation on the left to the representation on the right. I mean, first of all, does there even exist a computer program? And secondly, can we uniformly find it? And the answer in this case is yes. So this is some work with Dan Roy from a few years ago. So I'll say a bit more about the notion of computability that's relevant here. But the claim is that the distribution of an exchangeable sequence, the joint distribution of the infinite sequence, is computable in an appropriate sense if and only if there's some computable f that can be found uniformly in Y, such that these are equal in distribution, as in Finetti's theorem. And so the claim is that in this case, this hidden parallel structure can be automatically recovered in a way that exposes the conditional independence, even though, as we'll see, it involves some limiting quantity which is not obviously computable, and you might worry that you could code the halting problem into it. And in fact, in some higher dimensional cases, that does happen, as we'll see. Okay, so let me just tell you a bit about what these notions of computability are. These aren't going to define things carefully enough for some people perhaps, but hopefully will at least give you some intuition for a bunch of different perspectives. I should say, while all these different notions coincide in the case of computability, in the case of complexity theory, they often bifurcate in interesting ways. So some of this goes back to work of DeLu, Moore, Shannon, and Shapiro in the 50s, where they started looking at notions of probabilistic Turing machines and what notions of computability could look like for randomized computation. The formulation that I'm going to describe is essentially due to Schroeder in the early 2000s and the computable analysis community and this Weirach-style type 2 effectivity. And there's also been a lot of work in domain theory and elsewhere that's given essentially the same characterizations. So just to make this concrete, let's say we have a real random variable, and let's say f here is capital F is a distribution function. Then equivalent notions of this distribution being computable are that the probabilities are computable in the sense that this cumulative distribution function is computable at points of continuity. Another is that expectations are computable for a computable function from real to 0, 1, which implies that this is sort of continuous with a uniformly computable modulus of continuity. Another is what you might call computable simulation. This is saying that we can computably build random variables that have the appropriate distribution. So one way of formulating this is that there's some function from unit interval, thinking this is our sort of basic probability space, to the reals, such that when you plug in a uniform unit interval random variable to H, the distribution that you get out agrees on a measure 1 set with the distribution in question. It agrees in distribution with say the initial random variable. And so here it's essential that it be computable on a measure 1 set. It might be not just that it disagrees on measure 0, but that it doesn't even halt. If you imagine what's involved in well, so this is in terms of a uniform. You could also formulate this in terms of Cantor space. Say, let's say you have a sequence of coin flips and you're trying to build a Bernoulli of 1/3 random variable. There just are going to be, no matter how you do it, there will be at least one sequence of 0s and 1s that you're not going to be able to computably assign a value to.
Function from the reals to 0, 1, you mean on the rationals as a Turing computable, or other notions?
No. So here I mean something. So you can think of this as, say, a continuous function whose modulus of continuity is uniformly computable, or you can think of it in terms of, say, lazy real arithmetic. I give you an interval that the input's in, and you give me increasingly tight intervals on the output, and so on. So this you can take to be total in a way that this random variable might not be.
You don't have to be careful with your measure 1 set. It doesn't have to be itself computable.
Well, it will turn out it is. What I mean here is that there's some program describing H in terms of this interval arithmetic, and it happens that it converges on measure 1, and furthermore with measure 1 that agrees with the original. So it's only going to be able to have like its non-halting set be something like a pi2 set or something. Like it can't actually be an arbitrary function if it's being described by a program. But yeah.
The program might diverge exactly on the rationals. So I think I shared with Fokion's confusion about what the notion of computation is here, but it's just that I just don't know the notions of computation that are being used.
So I mean, there could be, say, a countably infinite set of points on which it diverges. I mean, in even simpler cases, or just imagine your distribution function is, the union, or let's say you have point masses, like geometric distribution on some uniformly computable set of values. Right. So actually, yeah, to take your example, you could have geometric distribution on the rationals under some enumeration, and then you're going to get the discontinuity exactly the rationals. But that's fine. I mean, that is the kind of thing that we can write all the time in computer programs, and it will. It is a reasonable notion of random computation, I think, which furthermore agrees with a lot of things that we do often. Now, you might say this is stronger than we need, that this sort of agreeing almost everywhere is more than we need in practice. And in fact, we'll come back to that at the end, a weaker notion which suffices for some of the cases where you actually can't get something this strong.
So
Yep.
Could you say what it means that real number is computable, like Turing machines, or I mean?
Yeah, so...
Yeah,
so I mean here, real, I'm not sure whether there's a particular real that's computable, but yeah, I mean a computable real in this sense is yeah, but I mean a computable real here is one for which, for example, we can uniformly give some rational that's within 2 to the minus n of it, or we can give a sequence of nested intervals that converges to it, or any of these equivalent notions. Okay, so we'll say that a random variable is computably distributed in any of these equivalent cases, and that its law is a computable distribution. And in fact, this can be extended to random variables in all sorts of other reasonable topological spaces, including things that are a little bit more exotic, like we'll in fact need to talk about computability of Finetti, like the space of probability measures on the reals under the weak topology. Right? If we're going to talk about a distribution on reals being computable, we'll need to have that notion. But this is in fact not only a natural notion which things line up, but as with this third point, it's exactly what we need in practice to be able to sample to arbitrary accuracy in the appropriate topology. Okay, so here's a somewhat different formulation of Finetti's theorem, which is going to be more useful for our purposes. So let's say we have an exchangeable sequence. Here I'm calling it x instead of y. So the sequence is conditionally ID given. So Finetti's theorem says that if it's exchangeable, then it is conditionally ID given some random variable, in fact, which we can take to be a random measure. We'll call it nu. And so one way of writing that is that the probability that the sequence lies in some Borel set on, say, reals to the omega, conditioned on this random measure is equal to the infinite product measure, almost surely. And moreover, this random measure nu is almost surely unique. In fact, we can even write a closed form for it that agrees almost everywhere. And so this is exactly this limiting frequency that we saw before, but generalized to the reals, say. So before we were saying that the long-run frequency of zeros and ones converges, the ratio of those. The only interesting Borel sets on a 2-point space are saying how many ones or how many zeros you have. But in general, take some Borel subset of the reals, B, and count how many times x1 through xn land there. Take the average of that for a fixed n. That limit exists almost surely. And in fact, if you collect up that information, that precisely describes a Borel probability measure, or a random measure, rather. And that random measure is exactly an object conditioned on which the sequence is ID, moreover, equal to that infinite product. Okay, so if you're used to seeing things like this before in the statistical literature, then this will be familiar. If not, don't worry about it too much. But this is a formulation that's going to be useful for us talking about the computability of it. And so the distribution of nu, so nu is a random measure, and its distribution is a measure on measures, a probability measure on probability measures on the reals. And that's what's sometimes called the mixing measure or the Finetti measure of the sequence X. So to take an example that's a bit different from the Polya-Urim, but sort of starting from the other side, what would it mean to start with a measure on a measure and then get an exchangeable sequence from that? Well, that's the easy direction for which you don't need Finetti's theorem. Let's say we have a bag of coins, some distribution on coin weights. We reach into the bag, pick a coin, flip it infinitely many times. That entire process, it's obviously conditionally IID. I mean, conditioned on that coin weight, it's IID. It's also easy to see that it's exchangeable, right? And more generally, what this is saying is that the only way that you can be exchangeable is if there is some bag of measures that does this. So you might have a random measure on the rails that you pick out of your bag and flip that in the sense of sampling it conditionally ID. But that's the only thing that can happen. So that's clearly exchangeable. The Finetti's theorem says that's the only way that that can happen. Okay. And so the result is saying that the mixing measure of an exchangeable sequence is uniformly computable in the sequence. So hopefully I've given you a taste of what's at least being stated here. I'll describe very briefly one of the ideas in the proof before moving on to another topic. Yeah? So what I mean by uniformly computable is it's not just that if I give you an exchangeable sequence, it has an exchangeable, that if I give you a computable exchangeable sequence, it has a computable mixing measure, is that there's a single program that given an appropriate representation, like for example the code on the left, it generates the code on the right. So a single program does that, not just it happening to be computable in each case. Is that done? No? Okay, so I'll just give you a brief sense of this and then move on. So one of the key ideas that's going on, so we're starting with the kind of thing that we can measure initially are these sort of sequence marginals. Given some sequence of sets A1 through AK, we can ask what's the probability to increasingly high accuracy that X1 lands in the first set and X2 lands in the second set and so on up to XK landing in the kth set. That's essentially the interface that we're given. I mean, we're given a program, but we're not going to be able to do a whole lot by some sort of static analysis of it. But by running it and paying attention to how its randomness is consumed, we can accumulate that information to ever greater accuracy. And and by classical Finetti's theorem, we do know there is some random measure nu sampled from this distribution on measures mu that we're trying to find, such that the xith term given nu is distributed according to nu. So there is this nu here such that this is equal to this quantity. But what we need to do in order to recover the Finetti measure, the mixing measure, which classically is equal to this, but which could be very poorly behaved. So this object here, I mean, if you try to get explicit bounds on it, you see that while it does converge in the limit, it's not at all obvious. It's just like pushing the problem down to another layer to ask for uniformly computable bounds on its convergence. But what we end up being able to do is approximate to ever greater accuracy certain mixed moments of the distribution. So we have a random measure, and here this set A is representing some interval in general. Let's say we have some finite union of intervals. What suffices to determine mu is to know, to increasing accuracy, the joint distribution on the what the random measure assigns as its value to all of these potential sets A. And you might think that, so it's essentially computing an expectation with respect to this indicator function of the set A, and you might think that this expectation is straightforward to compute, for example, by a Weierstrass approximation. Though even that, this Weierstrass approximation, the polynomials is essentially in terms of these quantities here, but it turns out to be not that simple because in order to get an arbitrarily good bound on this integral, well, some of the terms in the polynomials are going to be positive coefficients, some are going to be negative coefficients. You'll again have something that converges but without any control over which direction. And so it turns out that one way to do this, and the way that we first showed this, was essentially to work with Weierstrass approximations that you're guaranteed to have below at all points. And so in that way you can get sort of computably enumerable lower bounds on these integrals, and it turns out that that information suffices in aggregate because of how these quantities all have to sort of sum to one in an appropriate sense. So getting arbitrary lower bounds that you know are all lower bounds suffices. Thanks. Okay, so I'll now move on to the second problem, which is quite related to this. Just talk for a couple of minutes and then move on to some words about the final problem. So the second question is also about conditional independence. In fact, in a just higher dimensional generalization of this problem. So at first we were looking at sequences, yi, say, and the symmetry was exchangeability, which by definition is saying that the joint distribution of all the coordinates is equal in distribution to a permuted version of it. You could do an analogous thing for a two-dimensional array. There's now two natural notions already, which have been known in the literature as separate and joint exchangeability. So you can think of this as, say, some relational data. You have a two-dimensional array, maybe representing random values of a binary relation symbol. And so separate exchangeability is saying that there's two different if you take two different permutations, or possibly different, and apply them on the two coordinates, so essentially permuting the rows one way and permuting the columns in some other way, still that distribution will be invariant. Joint exchangeability is asserting that only with respect to the same distribution pi here. So this is an appropriate notion of exchangeability for something like an undirected graph's adjacency matrix. This separate exchangeability is maybe more relevant for something like a bipartite graph or just a general relation. Okay, and so if we take a look at the adjacency matrix of an undirected graph, here exchangeability is actually extremely natural. So in the sequence case, you have an exchangeable sequence when there's actually some symmetry property, right? Maybe you describe the sequence sequentially, but it turns out that the order didn't matter. But unless you actually just had a bag of objects that you were forced to label in some way, you might not start with something that was naturally exchangeable. But in the case of higher dimensions, it's actually very natural. If you have a graph that's not labeled and someone says, well, you have to label it to work with it in our framework, and you say, well, I don't care about the labeling, and say, choose any labeling, well, you might want to do this in a random way so that the labeling just doesn't matter, as was the case originally. And so if you have, say, a graph here, we only care about its isomorphism type. Here's the same graph up to isomorphism, but if you look carefully, you see the numbers are relabeled. These are the pictures of the adjacency matrix, where the zeros have been replaced by white squares and the ones by black. So it's kind of complicated compared to the one-dimensional case in that we have to consider these two essentially the same object because they're related by this permutation. I won't say more about this now, but it turns out that exchangeable graphs, if you haven't encountered them, they're used all over the place in Bayesian nonparametric statistics and various machine learning models, as well as in various combinatorics.
What's the difference between separately exchangeable and jointly exchangeable?
So here this tau need not have any relation to pi. So it's saying if you permute the coordinates of the rows and you permute the coordinates of the columns, you get the same thing in distribution. Joint exchangeability is only asserting this with respect to the same permutation. Okay, so the Aldous-Hoover-Kallenberg theorem, or this part is due to Aldous and Hoover. Kallenberg later showed Aldous and Hoover showed this for higher dimensions beyond 2, also in Kallenberg for unbounded arity relations and various other things, though we'll use a simpler case here. So you recall for exchangeable sequences, we had this representation that made the conditional independence explicit. And for the higher dimensional case, this is also essentially what's going on. There's some function such that a bunch of IID random variables, when plugged in, give you the same thing in distribution. Here the picture is quite a bit more complicated. I don't have time to go into tons of details, but let me give you some sense of what's going on. So let's say here we have random variables arranged in an infinite array. This goes on in both to the right and down. And if we look at the graphical model structure, the Bayes net structure of conditional independence for a sequential representation, it might look something like this, which is even more horrific, right? Let's say you first generate this, if it's generated sequentially in the sense that like xkl could depend on lower values than k and lower values than l or something like that. And what the Aldous-Hoover theorem is saying is that this kind of conditional independence is going on. So these are the random variables that are each IID and independent, each IID uniform that I didn't mention before. But here there's some theta which is shared by everything, and there's some randomness that each term can use on its own, like for that coin flip in the initial example. But then there's also separate randomness for each row and each column, which are shared across the row and column. So again, it's easy to see that this is conditionally IID, and not too hard, or almost definitionally, and it's easy to see that this is jointly exchangeable, separately exchangeable in this case, but in fact, Aldous-Hoover is asserting that given an exchangeable array, it must have a representation of this form with the conditional independence apparent. Okay, so the question again is, can we find this representation? And here the answer is a bit more complicated. So no is the answer in the same notion of computability that we had before. And the sort of object, along with Jeremy Avigad and Jason Root that we constructed, is something whose adjacency matrix from a distance looks like this in a certain sense. So, should actually go infinitely far in both directions. But what I mean by this is that if you sample an IID sequence of locations on each axis here and look at the induced graph, that is the random variable in question. So what is this construction? One way of viewing this, a bit more intuitive than just writing down an equation, is sort of infinite sequence of questionnaires for each user, which we think of as a row and a column. And the kth question has 2 to the k possible answers, and we add an edge between any 2 users if there's some question for which their answer agrees. So you might agree on the first question, which has 2 answers. You might also agree, even if you don't agree there, on the second question, which has 4 answers, or on the third question, which has 8 answers, and so on. So this is how we construct this object, but it's pretty straightforward to show that this object is not almost everywhere computable. There's not going to be some computable function that agrees with this on measure 1, essentially because given 2 questionnaires you can't accurately check in finite time. It's essentially a topological obstruction in the sense that there's no even almost everywhere continuous representation of this. On the other hand, as this construction pseudocode pretty clearly demonstrates, it's computably distributed as an array, essentially because if you want to get an arbitrarily good approximation, you just need to go some finite number of questions out, depending on what accuracy you want. So approximating this function suffices for sampling. So this function f here that's implicit in this picture, knowing it to a certain approximate accuracy in a way that we can computably do does suffice for sampling it. And so this is a sort of gap between the computability of the 2 sides of the representation here. Now the sort of silver lining here, or an alternative weaker notion than this AE computability, which does hold here of the representation when you have a computable sequence, at least in the case when, so there's a somewhat technical assumption I'm not going to get into here, but if it comes from essentially subsampling a picture here that's black and white, which is not the fully general case, then the distribution of exchangeable array is going to be computable if and only if there's this weaker notion of computable that applies to the representation f. So here, so we'll say that a function is computably measurable. You can think of the initial notion of AE computability as essentially taking continuity and asking for an effectivization of that. In that sense, this is an effectivization of measurability, if you think in terms of, say, Littlewood's principles. So here we're saying that uniformly in any positive epsilon, f is computable on a set of measure at least 1 minus epsilon. But as you change epsilon, even though there's a single program that uniformly does this in terms of epsilon, as you change epsilon, the answer it gives might not agree entirely with the answer it gave before. Okay? So this is a weaker notion, it turns out, and we can recover it in that sense, and that is essentially what suffices for sampling in appropriate cases. And so the end result here as to how computably we can represent the f here in this higher dimensional case. So for sequences, it's AE computable, but for arrays, it's not always AE computable, and sometimes even under additional nice technical assumptions, it's merely computably measurable, which says in a certain sense that a notion of approximation is necessary for capturing some of the structure that you might want to represent, for example, in a probabilistic programming language. So it's an interesting question that that I won't return too much here, but maybe Dan will have more to say about, or we're happy to chat about if people are interested in ways that this might play into language design. This is sort of weirder interface, this computable measurability. Even though you might consider it sufficient for your purposes, it's not the usual way that we're thinking of building randomness into a programming language where you give the accuracy that you want threaded through the entire program. But it might allow us to do certain sorts of transformations on code that we couldn't do otherwise. Okay, and it turns out that exchangeable arrays that don't have an almost everywhere computable f do appear in practice, not just in that sort of pathological example. So I won't say a whole lot about this, but there's certain points in the Bayesian nonparametrics literature especially where you do get an almost everywhere computable f, but then other natural cases where you don't. And in fact, if you look closely at the literature, you can sometimes see where this notion of approximation is creeping into the sampling procedures that people have for these objects. Okay, so I'm going to conclude with just a couple minutes about this third problem. And And so conditional distributions, everybody's familiar with this at some level, but in the case where you're not conditioning on a positive measure or discrete event, it's a little bit more complicated to say what you mean, even though there are various canonical ways of looking at it. This is a sort of way that Kallenberg frames it in his book, which I find kind of nice. You can think of conditioning as giving an L1 linear operator with certain properties on averages. It's also an appropriate Hilbert space projection. You can also, if you're familiar with radon-Nikodym derivatives, you can view it nicely in that way. And then the perspective that we're going to look at is disintegration. So the idea is you can essentially decompose things into a product measure that you integrate against one of the sides. So let's say you have a joint distribution represented on a rectangle. You want to disintegrate against one of the sides by saying, if I give you the value on that edge, you give me a distribution for that strip of the rectangle, such that even though it could have some measure zero wiggle room in what it reports, in aggregate, all the answers you report give you back the right thing upon integrating an arbitrary set. So now there is this issue that things are only defined up to null sets, and once you're in this realm, you need to be a bit more careful about what you even mean by getting the correct answer. But often people work in a setting where things are much more canonical. And one thing that people sort of tacitly assume that is often the case is that there's some version of this conditional distribution that is continuous. So you might be able to wiggle on a measure zero set to get a really pathological instance of it, but there's some way of changing a measure zero set such that you get a continuous version. And even in that context, it turns out that conditioning can be quite difficult and involve some limiting operations that allow you to code the halting problem. So the more basic operation, so also along with Nate Ackerman, we looked at conditioning on, say, the unit interval squared, a pair of computable random variables for which the conditional distribution is not computable. And then in this approximate sense, this computable measurable sense, or if you add appropriate noise to random variables rather, then you can sometimes get computability. And then there's a more technical result that I won't say much about, but if you do restrict to the case where there is a unique continuous disintegration, the setting that I was saying is actually quite common, if not explicit, in the statistical literature, then there's a sense in which this problem is uniformly equivalent to a sort of jump operator like the halting problem in an appropriate computable analysis setting. And in the setting where you don't have this, you can also say some things about it being about as bad as the halting problem. So I'll just tell you a little bit more about these first two results. So the first one saying that you have a pair of computable random variables, and in fact you can even take them to be absolutely continuous. The obstruction is not lying there, such that the joint distribution is computable, but the disintegration map in the sense of the function taking a single point to the conditional distribution of one variable given the other equal to that point is not computable. And this is the sense in which I meant that adding noise allows you to compute it. So if, for example, you have some additional computable random variable psi here, independent and absolutely continuous, then this conditional distribution, this is a notion of like an approximation to the conditional distribution. Now you might say, okay, that's great, that's all I care about, but I claim that that's actually not what you care about in some settings at least, because it just can't help. If you actually cared about this original object, a corollary immediately from these two is that you, of course, couldn't calculate a bound on the approximation error introduced by relaxing this condition to the one with noise. So if you can do this and you can't do this and you care about the first one, well then this is perhaps less consolation than you might think. Okay, so just a picture of the object. This is not absolutely continuous, though you can make it so by changing it. This is just simpler to describe. So this is all of the code where halting time of the nth Turing machine is sort of coded up here. So it is making use of recursion and lots of programming language features at some level, but it's a very simple set of random variables. So what's going on here is we divide the square representing the joint distribution up into strips. The level of gray is the density, roughly speaking. And what's going on here is that we run the 0th Turing machine until it possibly halt. So we run it for some number of steps. If it halts after that finite number of steps, we immediately make this tiled pattern with density 2/3 and 4/3 respectively, with 2 to the k pieces if it halts after k steps. So this one, for example, halted after after 3 steps, and hence there's these 8 pieces. This one, you can't tell if it halted after a very long number of steps or if it never halted. If it never halts, we make it gray, but in fact you can show that you can computably sample this in total even without answering that halting query, because essentially to compute like integrals of an arbitrary rectangle, you just need to know it approximated in that sense. And so on down the line. And then the key property is that if we look at a single vertical slice of this, well, that's going to code up the halting problem as a simple calculation shows. So basically if you look at any value other than a dyadic rational, and you take a look at the slice down there, you just read out whether or not it halted by whether you find 2/3 or 4/3 versus 1, the density in this region, say if it didn't halt. Okay, so this is a sort of encoding of the halting problem. Again, maybe we don't care about this particular pathological object, but this also means that if you're interested in, for example, extending a probabilistic programming language to a setting where you hope to be able to do conditioning automatically, you're not going to be able to do it in the fully general sense. You might, as in all sorts of, static analyses, looking for halting programs and so on, you might be able to carve out an increasingly rich set of special cases that cover a lot of what you care about in practice, but you just can't hope to do it uniformly in the same way that you can in the positive measure case. Okay, and I won't say anything more about these uniform results, except to say that you can essentially do these constructions in a way that, rather than building a single example, it shows that the problem of computing conditional distributions generally is about as hard as that example demonstrates. And so there's some interesting technical notions that go into it, and I'll skip that for now. So thanks for your attention, and I have a brief advertisement after that.
Thank you very much.
So if you're interested in probabilistic programming semantics, there's a workshop at Topple this year in Paris. A number of people in the room attended last year when I was in St. Petersburg. That was the first year, and actually quite a few people this week are even on the program committee. There are 2-page extended abstracts due at the end of this month, so if you're interested, I'll have some flyers out during the week, or come talk to me, or Avi Pfeffer, or Dan, or any number. There's quite a few people who have been there before or on the program committee, so I encourage you to take a look at that. Thanks.
Questions for Cameron?
Yep.
So you showed us several cases when you can compute the distribution and where the definite distribution was computable.
Mm-hmm.
Do you have any thoughts about the complexity of computing this distribution?
Yeah, so it's something that we've looked at a bit. So it seems that the complexity of the particular procedure that we give is probably pretty horrendous, but that's not to say that every possible way is. So what's going on here, we end up using very high degree polynomials to get any sort of reasonable accuracy on these moments in this sort of intermediate step. And so this particular construction is probably going to yield really horrible bounds. But it might be possible to do somewhat better in general. There's things that we've looked at. I guess there's no particular result to report. There's in fact even a simplified version of this that Dan had boiled down and Scott Aronson described on his blog a few years ago. A very simplified setting with binary sequences is just sort of a cute puzzle in complexity theory, and even that, it seems, is open. So, but yeah, it's a question that we're interested in. And I mean, there's some hints in the statistical literature from sort of classic bounds, like Dvoretsky, Kiefer, Wolfowitz, about like how quickly this quantity converges and things like that, which you could interpret as saying something about sample complexity. But yeah, maybe you have something to say, Dan.
I was just going to say that. So we don't know. So Cameron presented 2 notions of computability. One where you produce an exact sample. So that's AE computable, and another version where you're given a tolerance parameter epsilon and you produce an approximate sample. So in the latter notion, under some additional assumptions, like for example, if I tell you that mixing measure concentrates on a finite set of points, then we know the complexity is the same, but we don't know if it's the same if I demand that you produce an exact sample, so like a a computably measurable, so AE computable and computably measurable overlap in a sense if you take epsilon to be literally 0. So it seems that it could be impossible to get the complexity to be the same if epsilon's 0, but we don't, but that's wide open.
And you certainly wouldn't want to run in practice the particular thing we described. I mean, 10 pages of the paper amount to something that you could in principle write as code that provides a sort of funny, compiler trick, or, implementing this code transformation to get the parallel representation, but you certainly wouldn't want to do that in practice as it currently stands.
You mentioned in the beginning that there is a connection to graph limits, and those of us who have been since the beginning of the program, we heard a lot about graph limits from Jarek Nesetry.
Ah, yeah.
Can you tell us which of these results was the connection?
Yeah, so it's this setting here with Aldous Hoover, and you will hear a bit more about the connection between graph limits and Aldous Hoover theorem, at least in some sense, via Rahana Patel's talk, which was going to be today and is now scheduled for Thursday. But yeah, the general picture of what's going on, I guess it's also somewhat implicit in this picture here. Yeah. So you can view this as a graphon. So when I was saying take an IID sequence of locations on the unit interval and look at the induced adjacency matrix on those, that's essentially an instance of sampling from this as a graphon. So what's going on with Aldous Hoover is this representation here is kind of a complicated way of writing the graphon object. So if you're used to thinking of so the general statement is that if you have an exchangeable graph, which is a jointly exchangeable array in this sense, then you can write it as a mixture of sampling procedures over graphons for some distribution on graphons. So the ergodic case is a single graphon that you sample, and the general case is a mixture of them. And the graphon that's lurking in here is the one, so if you look at this, you see the graphon sampling procedure in disguise, because what's going on here, this theta is the mixture over possible graphons. Well, in the joint case, these V's are U's. So you have these UIs, which are the location on the unit interval you're sampling from, and then the randomness that's here is to implement the coin flip to do the Bernoulli of W of UI, UJ. So this is essentially the graphon sampling procedure. So what happened was Aldous and Hoover discovered this in the setting of arrays, and then Lovaas, Szegedy, and others rediscovered this in disguise in the case of looking at graphons. But yeah, so if you're interested in how this mapping works, there's a very nice survey by Diakonis and Janssen from a few years ago, maybe 2007 or 2008, that sort of builds a dictionary between these two perspectives.
One more question.
Is exchangeable sequences and conditional independence the same concept?
No, there's the different concepts a priori. One is a priori quite a bit stronger than the other, which is what makes one direction of Finetti's theorem surprising. So if we look at this version here, right? So exchangeability is just this invariance to permutation. Conditional independence is saying there's some random variable conditioned on which they're independent. And so if you have a conditionally independent sequence, like if I told you I have a bag of coins and that's how I generated it, it's easy to check that that must be exchangeable. But Finetti's theorem is saying that's the only way you can be exchangeable.
Is there anything you could say when you don't require all permutations to have invariance under all permutations, but say some subgroup of the symmetric group? Yes,
that's a great question. So this is something that has been called partial exchangeability, or there's various other notions. So going back quite a ways, I mean, first of all, you can even view the higher dimensional case as an instance of this, maybe like S infinity cross S infinity sitting inside S infinity if you sort of force the array into a sequence. But yeah, different subgroups have been considered explicitly over the years. People looked at like spherical symmetries. You get some representation in terms of Gaussians, and there's various other specific results. And then more recently, there's been work, including by Nate Ackerman and others, that's looked at general statements like Aldous Hoover for the case of like closed subgroups of S infinity and things like that.
So, is there a relation between the Finetti theorem and that family of results and martingale convergence?
Yeah, so I think there are some proofs of de Finetti's theorem that explicitly write down a martingale and use a standard martingale convergence theorem. I guess one hint about that is implicit here when I said you could first check that the limiting long-run frequency converges almost surely, that this slope almost surely is defined. And so some proofs of de Finetti's theorem, some of the less abstract ones, begin by first showing that you almost surely have a limiting slope, and then use that to construct the rest of the measure.
Thank you very much. So everyone is welcome to the reception in the lobby.